The Chameleon Eye cloud is dying, and inside that slow death, astronomers just found one of the richest troves of life-building chemistry ever detected in space. Nobody expected a cold, fading nursery of gas and dust to be hiding a treasure chest of frozen molecules that could one day become part of a living planet. Stick around, because the story of how the James Webb Space Telescope found this hidden treasure chest will change the way you think about where the ingredients of life actually come from. Before we go further, if discoveries like this get your brain buzzing, hit subscribe right now so you never miss the next chemical treasure hunt the moment scientists publish it. Chameleon the First sits about 500 light-years from Earth. A light-year is not a measure of time, it is a measure of distance. It is how far light travels in 1 year, and light moves fast enough to circle our entire planet 7 times in a single second. So 500 light-years away is a cloud of gas and dust, so cold and so dark that for most of human history, nobody even knew it was there. It looks like nothing. It looks like a smudge of ink on black paper. But inside that smudge, baby stars are being born right now wrapped in blankets of frozen dust. Here's the strange part. That same cloud is running out of time. Clouds like this one only have so much gas to give. Every star that forms inside it eats away at the material around it, and eventually the cloud thins out, gets blown apart by radiation, and stops making new stars altogether. Astronomers call this kind of cloud a star nursery because it is where stars are born, but a nursery that is slowly losing its ability to make more babies is also, in a very real sense, a nursery that is dying. And it is inside this dying nursery that James Webb found something nobody expected. Let us start from the beginning, because to understand why this discovery mattered so much, you need to understand what people used to believe about clouds like this one. Most people picture space as empty and cold, a kind of black nothing between the stars. That is the misconception. Space between stars is not empty at all. It is filled with thin clouds of gas and dust, and in the coldest, densest pockets of those clouds, something remarkable happens. Simple molecules freeze onto tiny grains of dust, the way frost forms on a cold window, and over thousands of years those frozen coatings can grow into something far more complex than anyone expected. For decades, scientists could only guess at what was frozen onto that dust. Ground-based telescopes could catch hints, faint fingerprints in the light, but the signals were too weak and too blurry to read clearly. It was like trying to read a note through a foggy window from across the street. Astronomers knew something was written on that dust. They just could not make out the words. That changed the moment the James Webb Space Telescope turned its mirror toward Chameleon 1. Webb is not a telescope that takes pretty pictures for the sake of pretty pictures. It is built to catch infrared light, a kind of light our eyes cannot see, the same kind of light that carries heat. Infrared light passes through dust clouds that would completely block ordinary visible light, the same way a heat lamp can warm your skin through a curtain that blocks the sun. That is what let Webb see straight into the frozen heart of this dying nursery, past the dust, into the ice itself. The first surprise came almost immediately. Scientists expected to find simple ices, mostly frozen water and frozen carbon dioxide, the same kind of stuff you would find in your freezer mixed with dry ice. What they actually found was a chemical mixture far more complicated than that. Buried in the ice around the baby stars of Chameleon 1 were frozen versions of methanol, ammonia, methane, and even more complex carbon-based molecules, some of them building blocks for the amino acids that make up proteins in every living thing on Earth. The surprise was not just that these molecules existed, it was that they existed in such large amounts, frozen and preserved like food sealed in a jar, waiting. Think about your own kitchen for a second. A bottle of vinegar on your counter and a can of frozen orange juice in your freezer are both just ordinary things you barely notice. But imagine finding that same variety, jars of preserved chemistry, sealed and waiting, 500 light-years away, drifting in a cloud of dust colder than anything in your freezer, colder than the inside of a glacier, hovering close to absolute zero, the coldest temperature physics allows. That contrast, kitchen shelf versus interstellar deep freeze, is exactly the kind of gap that made this discovery so stunning to the people who found it. Do you think a discovery like this deserves more attention than it usually gets? If you do, leave a comment and tell me what surprised you most so far, because your comments genuinely help me understand which parts of a story like this one you want me to dig into deeper next time. The team behind this discovery was led by astronomer Melissa McClure of Leiden Observatory in the Netherlands, working with a large international group of scientists using Webb as part of a research program nicknamed the Ice Age program. Their results were published in the journal Nature Astronomy in the year 2023, and the paper sent a ripple through the astronomy world because it was the deepest, clearest look anyone had ever taken at the frozen chemistry hiding inside a star-forming cloud. NASA and the European Space Agency, the two agencies that built and operate Webb together, both highlighted the findings as one of the clearest examples yet of Webb doing exactly what it was designed to do. Here is where the second finding comes in, and this one changed everything about how scientists think about where planets get their starting ingredients. Scientists expected these frozen molecules to stay locked in the dust forever, or at least for as long as the cloud existed, slowly drifting and eventually scattering into space, unused. What they actually found was different. The ice was sitting in exactly the right place, at exactly the right distance from the baby stars, to eventually get swept up into the swirling disks of material that surround young stars, the same kind of disks that go on to form planets. In other words, this frozen treasure chest is not just sitting in a museum case, untouched. It is sitting on a conveyor belt. As these young stars finish forming, gravity pulls the surrounding dust and gas into a flat spinning disk, the same basic shape a pizza dough takes when you spin it in the air. Any planets that form out of that disk will be built, at least in part, out of material that already contains the frozen chemical ingredients for the earliest steps toward life. Compress that idea down and you get something remarkable. Some of the raw material that could one day become part of a living planet was already frozen and waiting before that planet even existed. Scientists use a phrase for this kind of leftover material. They call it a fossil record, the same way a fossil in rock preserves a snapshot of ancient life on Earth. Except here, the fossil is chemical, frozen onto grains of dust, smaller than a speck of flour, preserving a snapshot of the raw ingredients available at the exact moment a solar system begins to take shape. That is why researchers reached for the word treasure chest to describe what Webb found. It is not simply that the chemistry is rich, it is that the chemistry has been sealed and preserved, untouched, since the very beginning of that system's formation. Let us slow down and talk about the numbers, because the numbers here are almost too strange to picture without help. The dust grains carrying this frozen chemistry are unbelievably small, roughly 1/10,000th of a millimeter across, smaller than a single grain of pollen, smaller than the smallest speck of dust floating in a sunbeam in your living room. And yet spread across the entire Chamaeleon-1 cloud, these grains add up to enough raw material to build thousands of stars and their surrounding planets. A single grain is nothing. Trillions upon trillions of them, drifting together across trillions of miles, become the raw material for entire worlds. The temperature inside that cloud sits at around 10 degrees above absolute zero, which works out to roughly negative 440 degrees Fahrenheit. For comparison, the coldest home freezer you own sits at around 0 degrees Fahrenheit. That means the ice inside Chamaeleon-1 is colder than your freezer by a factor of more than 400 degrees. At temperatures that extreme, chemical reactions that would normally happen in seconds on Earth instead creep along over thousands of years, molecule by molecule, atom by atom, slowly building complexity the way a single snowflake builds its pattern one tiny crystal at a time. There is something almost unbelievably slow and patient about that process, and it connects to the third discovery, the one that puzzled scientists the most. Scientists expected the chemical complexity of the ice to increase steadily and predictably the closer you got to the very center of the cloud, where the densest, coldest, most shielded material sits. What they actually found was uneven, patchy, almost random-looking pockets of extreme chemical richness, sitting right next to pockets that were comparatively plain and simple, sometimes only a short distance apart. It was like walking through a house expecting every room to be furnished the same way, and instead finding one room stacked floor to ceiling with treasure, while the room right next door sat nearly empty. Compress that surprise down to something familiar. It is a little like biting into what you think is a plain sheet cake, and discovering that only certain slices are hiding a rich, dense filling while the rest of the cake is exactly what you expected, plain and simple. Scientists still do not fully understand why the chemistry is distributed so unevenly through the cloud. Some researchers suspect it has to do with tiny local differences in radiation exposure, or subtle turbulence in the gas stirring things around unevenly, but this is still genuinely debated, and the models that predicted a smooth, even gradient of complexity simply did not match what Webb actually saw. There is another layer to this puzzle worth pausing on before we move forward. The instrument responsible for catching these ice signatures is called a spectrograph, which is really just a fancy word for a device that splits light apart into its individual colors. The same basic idea as a prism splitting sunlight into a rainbow, except Webb's version can split infrared light with a precision no prism on Earth could ever match. Every one of those tiny slices of color carries a clue, and stitching thousands of those clues together is what let researchers build a full inventory of the ice instead of just a rough guess. Building that inventory took an enormous amount of patient, careful work behind the scenes, work that rarely makes it into headlines. Researchers had to compare Webb's readings against laboratory experiments here on Earth, where scientists freeze known chemicals under conditions that mimic the extreme cold of deep space, then measure exactly which wavelengths of infrared light those frozen samples absorb. Only by matching the pattern from space against the pattern measured in a lab could the team confidently say, this dip in the light means methanol, this other dip means ammonia, this third dip means something far more complex sitting on the ice. Without that painstaking groundwork, the treasure chest would have stayed locked, its contents guessed at instead of known. This is the point in the story where I want to be honest with you about something. Scientists will tell you flat out that they do not fully understand every piece of this puzzle yet. They do not know exactly how much of this frozen chemistry survives the trip from cold cloud into swirling disk into finished planet. They do not know exactly how much gets destroyed by heat and radiation along the way, and how much makes it through intact. This is not a finished, wrapped-up story with a clean bow on top. It is an open case file, and Webb just handed scientists thousands of pages of brand new evidence to sort through. Would you share this video with someone you know who still thinks space is just empty blackness between the stars? Sharing helps this particular find reach people who have genuinely never heard that stars are born inside frozen chemical nurseries, and I think that is a detail worth spreading. Let us widen the lens for a moment and talk about scale, because this is where the story gets almost dizzying. Shamalion 1 itself stretches across a region of space that would take light more than 60 years to cross from one end to the other, and yet within that vast expanse, the specific molecules scientists identified are so small that a single teaspoon of ordinary table salt contains more individual grains than could ever be counted in a human lifetime. You have got a cloud so big, it makes entire solar systems look microscopic, built out of particles so small, they make a grain of sand look like a boulder. Holding both of those scales in your head at the same time is genuinely difficult, and that difficulty is part of why this discovery struck such a nerve in the scientific community. It helps to remember that Webb was not always guaranteed to succeed at a task like this. For years, this exact kind of observation, precise ice chemistry in a distant star-forming cloud, was considered a stretch goal. Earlier infrared telescopes, including the respected but limited Spitzer Space Telescope operated by NASA's Jet Propulsion Laboratory, could detect that ices existed out there, but lacked the sharpness and sensitivity to break the mixture apart into individual ingredients. Many researchers assumed a truly detailed ice inventory like this one would have to wait for an entirely new generation of ground-based instruments decades away. Webb was underestimated by some in exactly this narrow area, seen as primarily a telescope for distant galaxies and exoplanet atmospheres rather than a precision chemistry lab pointed at frozen dust. This result proved that assumption wrong in a single research program. The way Webb actually pulls this off is worth understanding because it explains why this data is so trustworthy. Webb does not photograph the ice directly. Instead, it watches the light from young forming stars shining out through the cloud around them. The way a flashlight shining through fog lets you see the shape of the fog itself. As that starlight passes through the icy dust, specific frozen molecules absorb very specific colors of infrared light, leaving behind a kind of barcode in the light that reaches Webb's instruments. Scientists then read that barcode, wavelength by wavelength, and match each dip and dent against laboratory measurements of known chemicals, essentially a fingerprint match performed across 500 light-years of empty space. That barcode reading process is where the exact numbers get almost eerie in their precision. Researchers were able to pin down absorption features at wavelengths measured down to hundredths of a micron, a unit so small that a human hair is roughly 70 microns thick. At that level of precision, scientists could distinguish frozen ethanol from frozen methanol, two molecules that differ by only a single carbon and hydrogen group, the chemical equivalent of telling apart two nearly identical twins from 500 light-years away, purely by the fingerprint each one leaves in starlight passing through ice. Here's a sound worth imagining for a second, even though nobody could ever actually hear it. If you could somehow shrink down and stand on one of those dust grains while a fresh layer of frozen gas settled onto its surface, there would be no sound at all, because sound needs air to travel through, and there is essentially no air out there, only a near-perfect vacuum. Just silence and cold, and a kind of frozen stillness stretching in every direction for trillions of miles. That silence is not empty, though. It is patient. It is the sound of chemistry working so slowly that human timescales barely register against it. Have you ever wondered whether the ingredients found in space really connect to the ingredients found in living things here on Earth? If that question interests you, tell me in the comments, because it genuinely shapes which topics I choose to research and explain in future videos. It is worth remembering just how young this entire field of study still is. Detailed ice chemistry like this was essentially impossible to measure with any real confidence before Webb launched at the very end of 2021. That means everything you have heard so far in this video is not decades-old textbook knowledge. It is closer to fresh evidence, still being argued over, refined, and double-checked by researchers around the world. You are not hearing about an old, settled chapter of astronomy. You are hearing about a chapter still being written, line by line, one observation at a time. There is a comparison worth sitting with before we move on, because it puts the disk conveyor belt idea into perspective. Think about the last time you watched someone knead bread dough, folding flour, water, and other ingredients together until they become one smooth mixture. The disk swirling around a young star does something similar on a scale that dwarfs anything in a kitchen, folding gas, dust, and frozen chemistry together over hundreds of thousands of years, until eventually that mixture clumps together into pebbles, then boulders, then full-sized planets. The frozen molecules Webb detected are not separate from that process. They are folded directly into the dough that eventually becomes a planet's crust, its oceans, and possibly its chemistry for life. Let us bring the story back down to something you can hold in your hands. Ethanol is the same basic molecule found in the alcohol used in some household cleaners and, in a different refined form, in beverages people drink. Acetic acid is the main ingredient in ordinary vinegar sitting in your kitchen cabinet right now. Formaldehyde, in tiny, careful amounts, gets used in certain manufacturing processes here on Earth. These are not exotic, alien substances invented for a science fiction movie. They are everyday chemicals, and Webb detected their frozen cousins locked in ice, drifting inside a dying star nursery, 500 light-years from your kitchen counter. That connection matters enormously, because it means the raw chemical starting point for a new solar system is not some mysterious substance unrelated to anything we know. It shares a chemical alphabet with the substances sitting in your refrigerator and under your sink right now. When our own solar system was forming roughly 4.5 billion years ago, it likely passed through a very similar frozen chemical stage, wrapped in ice built from nearly identical molecules. In a very real sense, Shamalian I today may be showing scientists a living snapshot of what our own solar system's baby pictures would have looked like if anyone had been around with a camera billions of years ago to take them. Scientists are careful, and rightly so, not to say this proves life exists anywhere else. Finding the frozen ingredients for amino acids is not the same as finding life itself, not even close. It is more like finding a fully stocked pantry sitting in an empty house. The pantry does not prove anyone is home, and it does not even prove anyone will ever move in. But a pantry stocked with the right ingredients absolutely improves the odds that a proper meal could eventually get made, if the right conditions come together at the right time, in the right kitchen. There is a specific number that captures the odds involved here better than almost anything else. Astronomers estimate that Shamalian 1 alone could eventually produce several hundred new stars before it finishes dispersing, and many of those stars are expected to form their own surrounding disks of planet-building material. If even a modest fraction of those disks inherit the same rich frozen chemistry Webb detected, that means potentially hundreds of brand new planetary systems, each one starting life with a stocked pantry of the same basic ingredients found in living things on Earth. Multiply that pattern across the billions of similar star-forming clouds scattered throughout our galaxy alone, and the sheer scale of the possibility becomes almost impossible to hold steady in your mind. And yet, all of that possibility is happening inside a cloud that is actively dying. Nearby, massive young stars, some of them dozens of times heavier than our Sun, blast the surrounding cloud with intense, ultraviolet radiation and fierce stellar winds, streams of charged particles racing outward at hundreds of miles per second. Over time, that radiation and wind erode the cloud from the outside in, the way wind and rain slowly wear down a sandcastle left too close to the tide. Eventually, within a few million years, astronomers expect Chamaeleon 1 to thin out so much that it can no longer collapse and form new stars at all. A few million years sounds like an enormous stretch of time from where we sit, and in a human sense, it absolutely is. But compared to the age of our galaxy, which stretches back more than 10 billion years, a few million years is closer to the length of a single afternoon compared to an entire human lifetime. In cosmic terms, Chamaeleon 1 is not just dying, it is dying quickly, on a countdown clock that is already ticking, which is exactly why catching this treasure chest of chemistry now, while it still exists, mattered so much to the scientists racing to document it. That urgency is part of what makes this particular Webb observation feel less like routine data collection and more like a rescue mission. Researchers were not simply cataloging chemistry for the sake of a tidy scientific record. They were documenting a fleeting chemical inheritance before the very cloud that produced it finishes scattering into the wider galaxy, forever losing the tightly packed density needed to make this kind of detailed measurement possible ever again in that exact spot. Before we head toward the end of this story, would you consider liking this video and telling me in a single sentence why a discovery like this one matters to you? Liking the video helps the wider YouTube system understand that content like this genuinely holds value for viewers like you, and that directly affects who gets to see it next. It also helps to understand why a cloud like Chamaeleon 1 was chosen for this observation in the first place, out of the countless dark clouds scattered across the galaxy. Astronomers picked it partly because it sits relatively close to Earth, at least on a cosmic scale, and partly because earlier, blurrier observations had already hinted that something chemically interesting might be hiding there, waiting for a sharper instrument to confirm it. In many ways, Chamaeleon 1 had been quietly underestimated for years, treated as just one more unremarkable patch of dust among thousands of similar patches scattered across the southern sky, noted in catalogs but rarely singled out for deep investigation. Webb is what finally proved that assumption wrong, turning an overlooked smudge into one of the most talked about dark clouds in modern astronomy. The team also had to account for something easy to overlook: contamination from Earth itself. Every telescope on the ground, no matter how well built, has to peer through our own atmosphere, which carries its own water vapor, its own carbon dioxide, and its own chemical fingerprints that can blur or completely mask the faint signals coming from deep space. Webb solves that problem simply by not being on the ground at all. It orbits roughly 1 million miles from Earth, far beyond the Moon, sitting in a gravitationally stable spot where sunlight, Earth light, and moonlight can all be blocked by a single carefully angled sun shield the size of a tennis court. That distance and that shielding are exactly what let Webb's instruments stay cold and steady enough to catch a signal as faint as frozen chemistry drifting 500 light-years away. Scientists are already planning follow-up observations, aiming Webb at other nearby dark clouds to see whether Chamaeleon 1 is a rare exception or a completely normal chemical stage that most star-forming regions pass through. Early hints suggest it may be closer to normal than rare, which would mean that stocked pantries like this one are not some cosmic accident unique to one lucky cloud. They may be an ordinary, almost routine step in how solar systems get built everywhere across the galaxy, quietly repeating itself in dying nursery after dying nursery, largely unnoticed until a telescope powerful enough finally learned how to read the frozen fingerprints hidden in the dark. Caltech, which manages Webb's Science Operations Center alongside the Space Telescope Science Institute in Baltimore, has already flagged several additional dark clouds for upcoming observation cycles, hoping to build a broader chemical map across many different star-forming regions at once. If that map confirms what researchers suspect, it would mean the treasure chest hiding inside Chamaeleon 1 is not a strange exception written in the margins of the galaxy's story. It would be closer to the opening paragraph, repeated with small variations, in the origin story of countless solar systems still waiting to be born. Few people walking around today have ever heard that a dying cloud of gas and dust can hold a frozen pantry stocked with the same basic chemical ingredients found in a bottle of vinegar or a can of frozen orange juice. That single fact, sitting quietly in a research paper most people will never read, connects the coldest, darkest corner of a star-forming cloud directly to the ordinary chemistry sitting in your own kitchen right now. That connection is not a coincidence. It is a thread, stretched across 500 light-years, tying the raw material of distant unborn planets to the raw material already sitting on your own countertop. We started this video with a paradox, a nursery that is dying and yet somehow overflowing with treasure at the exact same time. Now you understand why both halves of that sentence are true at once. The dying part is real, the cloud is thinning, the radiation is eroding it, the clock really is ticking down toward the day it can no longer form new stars. And the treasure part is equally real, frozen, preserved, and waiting on grains of dust smaller than pollen, holding chemistry that connects directly to the ingredients found in living things. What once felt like an empty, frozen patch of the night sky now carries a very different kind of weight. It is not just gas and dust drifting in the dark. It is a pantry, stocked over thousands of patient years, waiting to be swept up into new worlds before the shelf finally closes for good. Somewhere out there tonight, in a cloud you cannot see with your own eyes, that same slow, cold chemistry is still happening, one frozen molecule at a time, indifferent to whether anyone on Earth is paying attention. We are paying attention now. Scientists spent decades wondering what was written on that frozen dust, and Webb finally read the note. It said, in its own quiet chemical language, that the ingredients for something like life are more common, more patient, and more widely scattered across our galaxy than almost anyone dared to assume. That is not a small thing to carry with you after watching a video like this one. It is worth sitting with for a moment before you scroll on to whatever comes next. So here is the thought I want to leave you with tonight. Somewhere above you right now, invisible in the dark, a dying cloud of dust is quietly finishing a pantry it will never get to use itself, stocking shelves for a house that has not been built yet, for a family that does not exist yet, on the off chance that someday, somewhere, it will matter. That is worth remembering the next time you look up at a sky that seems empty. It never really was.